Here we have a system of equations, and we're going to follow the same methods we've already developed for systems of equations. And everything is going to come out very similar to what we did before. The only difference is going to be that in previous exercises we got real solutions, and we got two real solutions. We haven't yet confronted repeated solutions. You'll love that. Okay, but in this case we're not going to get two real solutions, we're going to get two complex solutions. And those solutions are going to be conjugates, which is going to be very convenient. It's actually going to save us work. The solutions are always going to be conjugates. It goes back to the fundamental theorem of algebra. Factor any polynomial into linear and quadratic factors. The linear factors all give you real solutions. The quadratic factors all give you complex conjugate solutions. Okay. And the quadratic factors, of course, are the quadratic factors that are irreducible over the real numbers. Okay, otherwise you would get two linear factors and you wouldn't just break down to quadratic factors. Okay, well, we talk about that. That's more than you need to think about right now, but it's something you should know from pre-calculus. Okay, so here's our system. We can write the system like this. If we multiply this row by this column, we get this, and that's going to equal this row, which will be y1 prime, so we get the first equation. This row times the column gives us y2 prime. It's all very straightforward. So our equation is y prime equals a y, where a is this matrix. Now we're going to assume, because we have to assume a solution, in a way very similar to what we've done with second order equations and second order homogeneous equations in this case with constant coefficients. We always assume a solution that's a multiple of e to the lambda t, or e to the rt. We use lambda here. But it's just very similar to what we did. It's some constant times e to the rt when we're doing second order linear equations with constant coefficients. Now, we're doing systems of equations, so our constant is not going to just be like an a e to the rt. It's going to be an x vector times e to the lambda t. The x vector being a constant vector, a vector x1, x2. And just as before, to get a particular solution, or a solution to fit initial conditions, we have to evaluate our constant a in a e to the rt. In this case, and it's not exactly analogous, but in this case, whether we're trying to solve for initial conditions or not, we're going to have to find our constant x1, x2, our constant vector x1, x2. So the analogy is not perfect, but again, think of this as being a constant vector that you're going to have to evaluate once you find values of lambda. Okay, so, well then our y1, y2, our solution, and we generally denote that solution with a vector. I didn't do this in class, but let's write it. So I'm going to write y. I'm going to write it as a vector, big fancy y vector. That's our y1, y2 column vector. And we're assuming that's of the form e to the lambda t times some pair of constant numbers, okay? And incidentally, that pair of constant numbers isn't unique, but it is unique up to a constant factor. Then, you know, if you're reviewing this, you'll understand what I mean by that. If you're seeing it for the first time, well, you should have been in class, and I think everybody was, so you've seen it still. You'll see what that means. Okay, so, well, we go through, I've got 3 dots here. You know, a miracle occurs, and we come up with a condition that the determinant of a minus lambda I equals 0. Okay, this is what's required in order for the e to the lambda t x1 times x1, x2 vector to satisfy this equation. This is your A matrix, lambda times the I equals 0. Now, I did go through this in some detail, I think in the class just before this one. So you want to understand those details. But I say there's good, better, best. Good is you cut to this, you'll be okay. Better and best is you understand the steps that take you from this to this, so you never fail to understand why you get to this, so that you never screw up and forget this, okay? That's ideal. Okay, do your best. Okay, anyhow, you get the determinant of a minus lambda I equals 0, and that's very simple. You know, let's see, do I actually do this? I've written this here. And I'm not, I mean, I know what that's in relation to, but I think we just then go up here, okay? The A is this, subtract lambda I, well, you're going to subtract a lambda here and a lambda here. Then you're going to get this. And this is something we're used to if we've done the equations with real solutions. It's so far identical to everything that we would do before. We get our characteristic equation, and then we solve the characteristic equation. Now, first thing we do when we see this equation is we check the discriminant. Okay, this is a lambda squared plus b lambda plus c. The discriminant, the square root of b squared minus 4ac. And that's going to be, well, b is negative 2 squared, that's 4. But 4ac, a is 1, c is 3, and 4 times 3 is 12. So we're going to get 4 minus 12. Well, right here, I've written it out, of course. Here's our discriminant. We can predict that we're going to have to use the quadratic formula because our discriminant in the first place involves a square, well, this discriminant is negative 8, so we're going to have to take a square root of negative 8. We can't calculate that exactly. We're going to have to factor that into 2 times the square root of 2 and do all kinds of things. So we're tipped off to the fact that we better use the quadratic formula. And we use the quadratic formula to find the roots, and we will, in fact, anytime we have complex roots, we're going to find complex conjugate because it comes right out of the plus or minus in the quadratic formula. So we have 1 plus or minus the square root of 2i, and that's our value. Those are our two values of lambda. So our equation is y1, y2 prime equals, well, okay, let's just evaluate this, okay. As a matter of fact, let's stop right here, and then we'll go into this. And we actually complete it over here, so I'm going to move the boards a little bit so that we can choose one of our eigenvalues and find our eigenvector and proceed to a solution.